Hello, my name's Jason with Remote Energy, and let's talk a little bit about wires and their electrical connection. Some of the things we want to talk about is how to pick the right wire for the job. There's a couple different types of conductors and many different types of insulation that covers that conductor. So we want to know, how do we figure that out, and where can we go to look to also figure that out? There's two main conductor types, stranded or solid wire. And we want to use stranded wire if there's the possibility for that wire to move at all. Because if we were to use a solid wire and it moved, then there's the possibility of there being a soft spot or a small crink in the wire that eventually could lead to high resistance or the beginning of a break in the wire. As far as the conductor material, we also have two choices, and that's between copper wire or aluminum wire. Aluminum wire has a higher resistance, so we need to use a larger diameter wire to carry the same amount of current that the copper wire could use. With insulation ratings, there's many different types of plastics that can be used as an insulation over our conductor. And we want to make sure that we pick the right insulation for the job that that wire needs to do. So where commonly are wires in a PV system? Well, usually from the PV panel to some kind of junction box, and then from that junction box we need to get to a circuit breaker before it goes into a charge controller. And different parts of the system require different types of wire. So you can see a bunch of letters there in the middle, the THWN-2. Each of those letters represents a different function of the insulation around the wire, and we're going to get into that momentarily. But looking at that THWN-2, that's a single conductor type wire, and it's usually used somewhere in conduit. So it can't be out in the sunshine because that outer layer will crack and peel off, and then the rain or the other elements can get through that softer plastic into the wire. But that USE-2, also called PV wire, well, that's rated to be out in the sun and the water, and it can take that high temperature. So let's try to pick the right type of wire for the job that we want that wire to do. On the outside of the insulation, there's a bunch of letters that are going to be marked on there. And these letters all represent a different quality of that insulation over the conductor. And remember that a conductor might have multiple different ratings on the same wire. So maybe that wire has a THHN rating and a THWN-2, because the wire manufacturers want their wire to be used in as many different locations as possible so that they can sell more wire. So a couple of these abbreviations here. We can see the H stands for a higher heat rated, or an HH is even higher rated. U would represent an underground location, or also called direct burial. This W represents it can be located in a wet place, but not submersed. So it's not submersible rated, but it can get a little bit wet now and again. There's our -2, which is our higher temp rated and wet location in the same go, which is nice. And there's our UF again, our NM, our non-metallic. That's usually used inside of a wall cavity. And tray cable, TC, which is usually a flexible conductor that has an outer sheath over all the conductors, so it's kind of double sheathed. We talked about what the letters represent on the marked on the insulation of the wire. And so here's a chart from the National Electrical Code, which is commonly used in the United States, where I'm talking to you from. And it shows the different ambient temperatures and the insulation rating, and then how much current we can run through that wire with the different insulations on there. And so the left-hand side, the columns are showing the diameter of the conductors in millimeters squared, or American wire gauge size, the AWG. And you'll notice at the top it starts with a number 14, so that's 14 gauge wire. And as the diameter of the wire gets larger, the numbers will go down. So an 8 gauge wire has a larger diameter than a 14 gauge wire until we get down to 4 gauge, 2 gauge, 1 gauge. When we hit 0, then it starts counting up with 1 aught, 2 aught, 3 aught as the diameter of the conductor gets larger. The insulation will most likely be thicker on the 90C degree type, which has advantages and disadvantages. Maybe I'm trying to pull many wires through a conduit, and if that insulation is thicker, the code will tell me I can only pull so many wires through that conduit with that thicker insulation. Well, there might be an advantage to using that thicker insulation because I can run more current through that wire, and it might be less expensive in the long run instead of pulling more wires. So now that we've picked the right wire for what we want to do with it, we're going to need to make connections on both sides of that wire. And we're going to want to make a connection that's going to last a really, really long time. So we want to make sure that we are getting all the strands of the wire inside of the connection. And in that lower picture, you can see one strand is sticking out of that bus bar with a set screw. And when I was an apprentice, the electrician I was working with saw that I had done that, and he said, you know what, if you can't get all the strands of that wire into that hole, you might want to pick a different profession. So ever since then, I've thought, yes, I'm rushing, I'm trying to get this job done, but let's make sure that we get all those strands inside of that set screw. When we're stripping the insulation off of the conductor, it's very easy to nick one of those strands of wire, and then we can't run as many amps or current through that wire because it's lost some of the diameter. So we want to make sure that we take the insulation off, but we don't nick the wires. Now I said take the insulation off because if you don't do that, if you just strip a little bit of insulation so there's only a little copper showing, and you push that into your set screw connection, maybe you're actually setting the screw on the plastic insulation and not the copper. So strip it correctly and get the correct amount of copper under the lug. We also want to make sure that it's torqued down with your screwdriver to the specifications that's in your panel board. And then also we want to make sure that we're doing the connection in the right way and that we're not putting two conductors of different diameters under the same screw. So we've run our wire. Now we need to make connections on each side of that wire that are in really good shape. So we're going to make sure that we use some kind of approved method to make sure those wires are connected. What we don't want to do is make a poor connection that could over time build up a lot of resistance. If you have a loose wire or one that potentially could arc, that could cause big problems in the future for that system. Here's an example of wires being landed on an overcurrent protection device, a circuit breaker. So often on the side of the circuit breaker is a gauge that will tell you how much of the insulation to strip off so that there's the correct amount that goes into the set screw on the circuit breaker. Looking at the slide on the right-hand side, there's two purple wires going in there, and the purple wire on the left, that's just about right there. You can see there's just a little bit of copper showing under the set screw. But on the right-hand side, that's a little much of copper being exposed underneath that set screw. Here's an example of the wrong way to put wires into a bus bar. The manufacturer of the bus bar has decided they want a certain amount of torque put on the wires that are put in each of those holes. And copper's pretty soft, and so we just want to make sure that we follow the recommendations of the bus bar manufacturer. And the picture on the left, they say, you know what, we really only want one wire into each of those holes. And the picture on the right is showing a few different problems, one of which is some of the wires just didn't really make it into the hole. So we've talked about taking the insulation off of the conductor. How do we do that? Well, this is a great picture of a wire stripper, and you can see vertically on the middle picture there's different sizes of holes there, and that's for different gauges of wire. And so if you pick the appropriate hole for the diameter of the wire, you can softly pinch your insulation, give it a couple half twists, and pull that insulation off of the wire. It takes a couple times to get a feel for it, and you can see the picture on the upper left there. That nick was caused by just pressing a little too hard. And it doesn't look like such a big deal, but if you put that wire into some kind of bus bar or set screw on the bottom of your circuit breaker and just wiggle it a couple times, that little nick could open up quite a bit, and that could cause a real problem, a high resistance. Lower left-hand side, we see, yep, got a little nicked on that one too, and a couple strands are sitting on the tabletop there. Here's another example of terminating the wire onto a set screw. The left-hand picture is showing just the perfect amount of copper showing there. And then you insert it in the middle picture into that set screw, and that's really nice. No insulation being crimped underneath the set screw. But unfortunately, that picture on the right, you can see a bunch of strands are sticking out there. And they might be even long enough to reach a bus bar on the other side and make a short, which we really don't want. We've been talking about putting the wire into different set screw connections, but often you'll want to add some kind of crimp connection on the end. So here's an example of some connectors you might want to use, and also the different plastic colors and coverings that you have. Now those colors represent the diameter of the barrel that you would press the wire into before you crimp it, with red being the smallest diameter, moving up to blue, and then yellow is often used for a number 12 or a number 10 American wire gauge size. We want to make sure that we use the right type of crimper and we use it correctly. The picture on the right shows a pretty good looking crimp. Those wires all made it in there, and you can see the slot in the top of that crimp isn't open very wide. It's real flat. Sometimes if you use a handheld crimper in the wrong way, you'll open up that crease in the barrel and it won't smush the wire very well, which is what we're trying to do. So let's make sure we're using the right crimper, that it's listed for the lugs that you'll be crimping on there. And battery crimps are a place where we've seen a lot of failures. This picture on the upper right shows this crimp might have been done with a hammer or a pair of vice grips. And the picture on the left is showing where that crimp just failed. You can see when the wire came right out of there, which causes a really bad connection. Now, these are flooded lead acid batteries. You can see the red cap on top, where you can put distilled water in. And when these batteries are charging very heavily, they're producing some hydrogen sulfide gas, which is somewhat explosive. And if it was in a closed container and you have a connection that potentially could be arcing or sparking during that period when it's charging very heavily, there's a real low chance, but potentially that could cause a little explosion, and we really don't want that to happen. So we're going to always crimp with the correct tools, and then we're going to check it. We're going to tug test that wire to make sure there's no possible way we can pull it out and that there's a good connection there. So after we have our properly done battery cable crimp, we want to make sure that we install it correctly. So these pictures are of an inverter, and the picture on the left shows that a washer got put between the battery cable lug and the inverter base. Well, there's a lot of current potentially going through there, so we want to do it like is shown on the right hand side, where the lug goes right against the inverter base, and then there's a flat washer, and then there's a lock washer, and then your nut. So that lock washer is helping maintain the proper tension, the proper torque for that battery cable lug to press against the inverter base. So there's a really good connection there. And when that cable is cooling and then getting heated up with the amount of current going in or not going in, there can be a lot of contraction and expansion between that copper plated lug and the stainless bolt that's attached to the inverter. So that lock washer can help quite a bit, helping to make sure that that connection stays solid for a really long time. So thanks so much for listening to our presentation here on wires and their connections, and hopefully we'll be able to talk more soon.